Welcome back to our series on multivariable calculus. In this episode, we're going to talk about arc length, particularly the length of a vector function. Up to this point, we have looked at distance between points and lengths of vectors. And of course, those are easy to calculate along a straight line. Even a three-dimensional vector's magnitude could be easily handled by the Pythagorean theorem. But when it comes to a curved path, we're going to have to change our technique. The distance between individual points on this curve can represent somewhat the path that was taken. The problem is these straight line vectors in this curve don't match up. Even if we found, say, the tangent vector at this point, which would be r prime of t. Its magnitude would basically tell us how far down the path it goes. So if we took its magnitude, we could say multiply that by a small segment delta t in order to figure out how long it was, say, from one point on the curve to another. Of course, we'd have to recalculate r prime of t as we moved, and the shorter we make the delta t segments, the more accurate the slope will actually match the tangent to the curve. What it means is doing basically an infinite series. This series will start with the idea that we're going to vary I from 0 to n. We're going to break this interval up into n equal parts. And then we're going to add on r prime of t's magnitude times the delta t interval. And we're going to do that as often as we can, breaking this into 10 pieces and 20 and 30. Basically, the more pieces we break it into, the better the slope or the direction of the tangent curve will match at that point. And of course, the smaller the delta t intervals we'll get. Basically, we want to calculate this under the limit as n goes to infinity, so that we're taking more and more pieces. Of course, when we do all that, we're going to end up with an integral. This will be the integral from a to b of the magnitude of the tangent vector, r prime of t, dt. Now, I'd like to say this integral is always easy to calculate, but of course, frequently it won't be. Keep in mind that the magnitude of r prime of t will itself be a function that contains three parts. The derivatives of the three components, those will each be squared and added together, and then they'll be placed under a square root. That could, in fact, turn out to be an integrand that's extremely difficult to evaluate with the techniques of integration that we know. So while in concept, finding the arc length, which is what this represents, the arc length, is easy in concept, it can at times be extremely challenging in practice. Let's do an example. The curve we want to pick on is a simple one whose length we already know. That way, it will serve as a good exercise for seeing if this technique really works. Basically, we'll use the curve cosine t sine t, which we know makes a circle in the xy plane centered at the origin with a radius of 1. Of course, the length of that arc is going to be the circumference of the circle, 2 pi. Well, let's see if this arc length formula actually produces 2 pi. There's rt, and again, it will form a graph that looks much like this. Well, the first derivative of rt, r prime of t, would be equal to negative sine t and cosine of t. Further, the magnitude of r prime t would then be equal to sine squared t plus cosine squared t, all under the radical. And of course, this is equal to 1, and the square root of 1 is equal to 1. That means the integrand for our integral for arc length is just going to be 1. In this case, turns out not to be too terrible. So the arc length will equal the integral now for our particular function. We want to do 1 lap around the circle, 1 full circumference. So that's going to be from the angle 0 all the way around till the angle 2 pi. So 0 to 2 pi. The integrand is 1 dt, and of course, that's going to be t evaluated between 0 and 2 pi, and that's going to produce the answer 2 pi. So indeed, the formula works as long as the integrand is easy to evaluate. This will be a good technique for finding arc length. Now this will apply to all of our vector valued functions. We'll be able to find the length between any 2 points on the arc. There's really only one caveat and only one little asterisk that I'll add to this, and that is this formula implies that in covering the arc length from A to B, that the curve doesn't turn back upon itself. If in going from A to B, it would suddenly stop and move backwards for a little bit and then move forwards again, eventually reaching B, the arc length from A to B would only take into account the actual distance traveled. If it backtracks and then retraces, that portion will turn out to be a negative length plus a positive length, which will cancel out in the overall length. And that's incorrect in terms of finding the arc length. If it does in fact backtrack, that should be encountered. So you'll always have to look for discontinuities like that within the range of the integral and determine whether you've got to do it from a piecewise basis. However, those sort of space curves should be fairly obvious. Okay, now it turns out that finding arc length is not a new concept for you. Everyone in their Calculus 2 course had to work through arc length formulas as part of your chapter on techniques of integration. Basically, you took two-dimensional curves, x and f of x, and based on the shape of the curve, you went ahead and found the length between two endpoints. Well, let's represent this as a space curve and see how this one formula will still generate that old formula that you used last year. Okay, if we were going to represent this as a space curve, then that space curve would be r of t is equal to its x component would be t and its y component would be f of t, matching this particular f of x that produced this curve. That would be the vector we would use. It would only be two-dimensional. Well, let's go ahead then and apply the formula for turning this into an arc length. I need r prime of t, and in this case that would be 1 and f prime of t. And then I would need to find the magnitude of r prime of t. And of course, the magnitude is its x component squared plus its y component squared, and that whole thing under the radical. And then in order to find arc length, I need to take the integral between the endpoints of that magnitude dt. And of course, there's the integrand. It would be the integral from a to b of the square root of 1 plus f of t prime squared dt. And I think you recognize this because this is the same arc length formula that you used in Calculus 2. I don't know how thorough the derivation was at the time, but you can certainly see where this formula comes from in terms of how we calculate arc length for a 3D vector function. That's about it in terms of arc length. Arc length stands on its own as a way to find distance covered if our vector valued formula is actually going to be representative of a physics displacement. What the arc length does is it actually determines how far you go in between your endpoints. Then of course, if we divide that by the time it took, it's a great way to find the speed because it would actually be the distance covered divided by the time. In addition, we're going to be using arc length in order to find our next main concept, which in the next video will be curvature.